Hello everybody and welcome to World Metrology Day 2020. Today I would like to talk about radiometric traceability for photobiological safety. Photobiological safety measurements of lamps and lamp systems are described in the measurement standard that you see referenced here. Within these standards, measurements roughly divide into two categories: irradiance and radiance measurements. Irradiance measurements associate to risks that are involving the skin or the surface of the human eye. Radiance measurements are associated to measurements that involve possible damage to the retina inside of the eye. In this presentation I will further talk about the first item that you see highlighted here, involving actinic UV of eye and skin. First, I would like to highlight two photobiological effects that can occur due to ultraviolet radiation. The first and most well known is referred to as ultraviolet erythema, also known as sunburn. It is induced by ultraviolet radiation, mainly in the wavelength range of 200 to 320 nanometers. The symptoms are pretty similar to sunburn, so reddening of the skin at the site of UV radiation exposure. The second photobiological effect that I would like to highlight is photokeratitis. It is also known as snow blindness. It occurs at the cornea of the human eye, and it is mainly induced by ultraviolet radiation in the wavelength range of 200 nanometer up to 320 nanometer. The symptoms can be a sensation of sand in the eye, sudden violent contraction of the eyelid muscle, cloudy vision, and a reaction in between the upper and the lower eyelid. To quantify the risk due to actinic UV, one needs to measure the spectral irradiance of a light source. Irradiance is usually expressed in power per unit of area. For actinic UV, the wavelength range is 200 to 400 nanometers. The actinic weighting function can be seen in the left-hand graph. Once the irradiance has been measured and weighted according to this function, one can calculate actinic doses. This doses is expressed in joule per square meters. In the graph at the right, you can see the maximum allowed irradiance as a function of time. So what kind of traceability is needed here? The main unit involved here is spectral irradiance, which is power per unit of area, and it is typically expressed in watts per square meters. Devices that measure this quantity are detectors or spectral radiometers. They first have to be calibrated for spectral irradiance responsivity. So how do we provide traceability for spectral irradiance? First of all, we start with the unit of optical power. This is derived using an absolute cryogenic radiometer that you see here on the left. Then we also need to include area, so we need some length measurements. These are traceable to the frequency cone that you see here on the right. Combining those two, we can determine the spectral irradiance responsivity of a detector or a spectral radiometer. This device can then be used to measure the spectral irradiance in watts per square meters. Combining this with the unit of time, we can compute the doses. Then I would like to highlight an example of the need for reliable photobiological safety measurements. UVC is often used to disinfect air, surfaces, or to sterilize water. Due to the recent COVID-19 situation, we've seen increased interest in UVC radiation. But this UV radiation itself can pose a photobiological health risk. This risk can be quantified through traceable optical measurements. In this context, I would like to refer to a position statement that was recently released by the CAE and that you see referenced here at the bottom of the slide. The use of optical sources in UV can involve some photobiological risks. Both the effectiveness and the risks can be quantified through traceable optical measurements. With this, I would like to conclude my presentation. Thank you for your attention, and stay safe and stay healthy.